Hi everyone, in this video we're going to look at a dual solution example where we can understand the region as moving horizontally or vertically, meaning we can either go dy dx or dx dy. Problem says find the volume of the solid that lies under the paraboloid z equals x squared plus y squared and above the region D in the xy plane, which is bounded by the lines y equals 2x and the parabola y equals x squared. So let me do type 1 here, or let me set up both of these. So my region is y equals 2x and y equals x squared. So I have y equals x squared and I have y equals 2x. And what happens in this case is that I can take this region and I can actually set this up as being going vertically, and those are two different curves, and I can set this up as going horizontally. What would the setup look like? The only difference is, well, I still have x squared plus y squared. If I'm going in this direction, I have dy and then dx. Y's are easily represented here as 2x squared to x squared. I need to find this, and this is the solution to x squared equals 2x squared, which is positive 1. So this sets up, this is, sorry, I did something wrong. This is 2x, not squared. Solution to x squared equals 2x is at 2. So this is a 0 to 2. Whereas over here, the integrand is still x squared plus y squared. This is set up as now dx dy. So I got to express the x in terms of y, which means for this becomes x equals y over 2. And this becomes square root of y. And it goes from the line to the curve. So it goes from y over 2 to square root of y. And these have to be values of y. So I need this value. I know this is x equals 2. And when x equals 2, y equals 4. So this goes from 0 to 4. And the thing is, they will both give the same result. Now let's try it out. This becomes x squared y plus y cubed over 3, 2x to x squared. So I get x squared minus 2x plus 1/3 x to the 6 minus 8x cubed. Foiling things out, x to the 4 minus 2x cubed plus x to the 6 over 3 minus 8/3 x cubed. So x to the 6 over 3 combine, or let's keep them in decreasing order of powers of x, and taking the LCM here will give me a 14x cubed. Now don't forget that there's also a dx and then an integral from 0 to 2. Sorry, let's pause that here and see what's happening over here. Here the integral is with respect to x, so I get x cubed over 3 and a y squared x with the limits y over 2 and square root of y, which, let me use the radical notation, y 1/2. Sorry, the exponential notation. So plugging this in, I get y 3/2 1/3 minus y cubed over 8 plus y squared y 1/2 minus y over 2. So I get a 1/3 y to the 3/2 minus y cubed over 24 plus y to the 5/2 minus y cubed over 2. So combining some of these, specifically these two, I have a 1/3 y to the 3/2 plus y to the 5/2 minus 12, so 13 y cubed over 24, and then don't forget the dy going from 0 to 4. Now doing the integral, this is going to be 1 over 21 x to the 7 0 to 2, 1 over 5 x to the 5 0 to 2, and 14 over 12 x to the 4 0 to 2. So you get 1 over 21 times 128 plus 1 over 5 times 32 minus 7 over 6 times 16. What about here? Here we get a 1/3 y to the 5 halves divided by 5 halves, which becomes times 2/5, y to the 7/5 times 2/7, 13 over 24, y to the 4 over 4, and all of this is 0 to 4. So you get a 2 over 15, 4 raised to, so, okay, 4 raised to 5 halves. That's square root of 4 is 2, 2 raised to 5 is 32. 32. The 0 becomes a 0, so at least we are spared that here. 2 raised to 7 is 128, and 13 over 24, 4 raised to 4 over 4 is 64. So doing some simplification, 128 over 21, 32 over 5 minus 56 over 3, 64 over 15 plus 256 over 7, 12, 32, 16, 6, 3, 8, 104 over 3. LCM 105 times 3, so 315. That's going to go 15 times. 32, that's going to be 63 times, and 56, 105. This will also give 2315, 21 times, so 64 times 21 plus 45 times, 45, 256, and 105, 104. And if you evaluate both of these, they will give you the same result, which is 216 over 35. So which means in situations where it's possible, it's doable. And what does this look like in 3 dimension? Well, in 3 dimension, what you have is a paraboloid, and then you basically have this surface and y equals x squared and y equals 2x, something of that sort, this shaded region over here. Right, now another application of this fact that you can switch around x and y and still have the same result is that it can be used to evaluate some integrals which cannot directly be evaluated. So we'll look at an example what it means. Suppose I'm trying to evaluate this integral. The problem here is, as soon as I encounter this, I am stuck, because there is no way to evaluate this. And when I say there is no way to evaluate this, I don't mean that you don't have the tools. There is no way to evaluate this integral directly, but we can interpret this as a volume problem, as the region y, because it's dy, so it's y equals x to y equals 1, and x equals 0 to x equals 1. So it means that I am integrating along this region, and the fact that it is dy first means that I interpreted this as going vertically. Well, let me copy this before I do that. But I could look at it as going horizontally. That's still possible. As soon as I do that, my integral is now sine y squared dx dy. Where does x go from? It goes from 0 to this line, which can be written as x equals y. And where does y go from? 0 to 1. As soon as I do that, my first integral is now solvable because sine y squared is a constant. So I just get sine y squared x from 0 to y, which becomes y times sine y squared. So that my integral is 0 to 1 y sine y squared dy. Now this is not a problem because it's not just sine y squared. There's a y outside. So we can use a substitution to get du is 2y dy. Y dy is du over 2. 0 to 1. 1/2 sine u du. 1/2 negative cosine u 0 to 1. 1/2 negative cosine 1 plus cosine 0, which is 1. So it becomes 1/2 1 minus cosine 1. So this becomes a powerful tool because now this can be used to evaluate certain double integrals which may not be possible in one order, but is possible in another order. Last thing we're going to go over are some properties of double integrals, which are kind of obvious or helpful. Certainly is that if we have a region D and it has to be split into d1 d2 such that one goes in one you have to calculate it horizontally and one vertically, you can still do that because the integrals are additive in nature. If your function is bounded between two numbers m and n, the integrals are bounded between area times m and n. That's basically because of the area. So the rectangles that are bounding them have to be a figure might make it easy. So suppose I have a structure like this, right? Then the integral represents, suppose, and this is the minimum value it has, right? So that's the minimum value, and this is the maximum value it has. So that's m and that's n. It's basically saying that this double integral, which is the volume of this whole thing, is going to be more than the volume of the green thing, because that's the m times area of the base. But it's going to be less than the volume of the red thing because that is made up of a surface with the maximum height, so it covers more volume. And this is just a result that's sometimes used in some sort of approximation results. It's just helpful. Okay, last question, or which I'm going to give as an extra credit, is another situation where it's not directly solvable, but can be by order switch. So once again, this is an extra credit which you can submit via email or along with your notes submission. So when you submit the note for this section, you may or may not choose to complete this, and then depending on that you will get extra credit or not. That's pretty much it for this particular section. So we've covered double integrals over rectangles and general region at this point. That's all.